Okay. Hi, everyone. This is my first day in Seoul, so I might be a bit tired, but stick with me and I'll hope to make it short and brief. Today, I'll be talking about safety on the fly, scaling HA Reachability, which is a formal safety methods tool, for leveraging structure and by using online adaptation. So when do autonomous robots work well? And I'd argue that mainly they work well in very structured environments, devoid of other human beings being present, such as in a package sorting facility, or in settings where there is still enough structure and compliance to accept certain forms of failures. So here, the box where the robot has to insert its object gets moved. However, because the box is compliant, the robot's still able to achieve its goal. The reason it's wearing a hot dog is because it was Halloween, and so I don't know, but this is a good video that I found for that. Where robots really struggle is in the presence of humans and when faced with unexpected changes. And here, a proxy for the presence of humans is just having two Waymo cars next to each other, trying to figure out who merges first. And obviously, the idea would not be for the one car to pass the other to merge first. Like, that's not safe driving, even not in the US, where laws are a bit more all over the place. Or unexpected changes where a robot moves from a grassy patch to a concrete path and just fails immediately. And so these types of unexpected changes and retaining safety under these conditions are kind of the settings that I'm interested in. And for this, we'd have to look at two different types of uncertainties. So I'd split them into the unknown unknowns, which is termed generally as epistemic uncertainty, and the known unknowns. And examples of unknown unknowns are a new obstacle appearing in an environment, a sudden loss of actuation due to a motor or battery failure, or, for example, unmodeled wind gusts in the environment. Whereas the known unknowns would be the uncertainty over the output of a model, the uncertain yet still modelable disturbances in an environment, or the multimodality of the environment due to human-robot interaction. I will not have time to go into any of my human-robot interaction work today, but some of the other topics I'll discuss in two different thrusts here. But the core principle of what I'm interested in is on the decision-making side of things. So we have an existing perception module, we have an existing estimation and prediction pipeline, but what can we do on the decision-making side to make sure that we retain safety when faced with these uncertainties? And so I'll split this talk into three different thrusts. Thrust one is some of my early PhD work, where I focused on reacting to unmodeled changes in the environment, so reacting in real time and recovering safety as fast as possible. The second thrust is more on adapting offline learned value functions for online use in these environments where changes, but modelable changes, are present. And then the third thrust, which is kind of separate from this, but is a recent thrust that I've been working on and that I want to share some early work on, is scaling these formal safety tools by leveraging structure in either the problem setup or in the environment in one other way. So the background, I need to give some background on what the safety problem is that we're considering. So we have a dynamical system, X, with inputs U and a disturbance D, that are both in compact sets. They're measurable. These are all control theoretic tools. And we denote a trajectory starting at a point x0, t0, under control and disturbance signal U and D, over time t0 to t, by psi. And this will be useful just to get around to the point of what safety formally can be defined as. And you typically have an environment in which you have a set of obstacles which jointly define the failure set calligraphic F. And accompanying this failure set, we consider a constraint function L, which is defined such that L is negative only if that state is within the obstacle set. So with this in mind, how can we characterize and enforce safety? So first, characterizing safety. For characterizing safety, we need to think about a certain set of disturbances that we can consider in the environment. Because if you have a control policy that has to play first its entire game and show over the course of a control signal what actions it will take, obviously the disturbance can take actions by knowing what the controller will do in the future, which is typically not what we want to consider because that makes the disturbance signal too powerful. So instead, what we consider are these types of non-anticipative strategies where just the way you can think of it is after every control action gets taken for a discrete time system, the disturbance action complete. So it has an instantaneous advantage, but not an advantage over the entire time horizon. For a continuous time system, it has to be defined this way. For a discrete time system, you can just think of it of them playing one after the other. And then to characterize safety, we consider a control invariant set, which is a set such that for any state x0 that lies within this set, for all disturbance strategies, there exists a control signal over time such that the trajectory remains in this set C for all times. And so, for example, what it could look like is a trajectory that always can stay within this set, this green set here. So that's a formal way to characterize what safety is. And a way to do that is through value functions, where the idea is that the value function characterizes the difference between a safe region through a desired safety constraint. It combines this with the long-term effect of the dynamics into a single scalar function where its level being greater than 0 and also the amount that is greater than 0 provides a measure of the safety margin, and its gradient ideally provides a safe direction, so informs in which direction the system should move to get higher levels of safety. And this formal safety tool, Hamilton-Jacobi reachability, provides a way to characterize such a control invariant set through a value function. And so specifically, if we define the cost function for an avoid game, so where we want to avoid some failure set, as the minimum value of the cost function, of the constraint function, L, over a trajectory. So what is the closest along this trajectory that we've gotten to the failure set, basically? The value function is then defined such that we, as the controller, we try to maximize this cost in a way, so it's more of a reward, and a positive cost is avoiding failure. And the disturbance tries to minimize it. So it tries to drive you into these failure sets. So that's defined as such. And then the way to solve this problem is derived in the 1950s and 60s by Bellman and Isaacs, is framing this as a variational inequality. And basically, this posits a variational inequality is a richer form in a way of a PDE, which poses this problem with the Hamiltonian defined as such. So you have both a spatial gradient and a temporal gradient, and this can be easily solved using dynamic programming. Starting from at time 0 from the constraint set, a constraint function, and then over time refining that to obtain a value function that retains safety. However, we now have a value function that defines safety. What can we do with such value function to also make sure that the system stays safe? But first, before I jump into that, just some of the techniques to solve this variational inequality. The most classical one is spatial discretization of the state space and solve this variational inequality on the grid backwards in time. However, this scales poorly with the dimensionality of your system because you have to consider spatial discretization. Deep reach, which is a self-supervised learning technique, which uses this variational inequality as loss and uses curriculum learning to kind of guide the solution to have to minimize over time this loss. And it's a physics-informed neural network because obviously it uses this variational inequality as a physics term. And then reinforcement learning, where we have this safety-Bellman equation and we use discounting on top of it to ensure contraction. And then that can be deployed obviously using DQN, but also a soft actor critic or PPO. The reason I discuss all of these three is because I've worked with all of these three during the course of my PhD, and today we'll cover all of these three in different levels of detail. And then back to, once we have this value function, how do we use it in an online setting? And in an online setting, the way I always look at these problems is that you do not want to interfere with the other decision-making modules. You want to only interfere when necessary. So you have a suite of decision-making modules that output a control action that you want to take, which is U hat. And then this safety filter is there, where you want to minimize the difference between the U that you actually apply to the system and this nominal control that you want to apply, such that we are safe. And what does we are safe mean here? That's obviously very essential. Hope. This didn't really come out nice. Let me quickly try and improve that. Sorry. Oh, my screen froze as well. Ah, there we go. I don't know how that solved itself, but anyway, here we are. Specifically, we want to minimize the deviation such that the time derivative of this value function is greater than an exponential decay rate. So we do not want to, basically what this says is we only want to approach the safety boundary that we have at a certain rate, and basically at an exponentially decaying rate. And this is often defined as a control barrier function constraint, but it is applicable to any type of value function. So now we have both a way to characterize safety and to enforce safety. However, all of these methods are typically applied offline, where offline you characterize safety, and then online you enforce safety. And they're not very adaptable to changes online. So that's one of the first works during my PhD is how do you now react to these unmodeled changes in the environment? And for this, we consider first that we start, instead of starting from the constraint function L, we start with an approximately safe value function. Can be a learned CBF, can be some other type of approximate knowledge of what is safe and what is unsafe in the environment from, for example, imitation learning. And then instead of using the theoretical definition where we take the minimum of the trajectory over time and its associated variational inequality, we now initialize this function, and I don't have a pointer, maybe I do. Let me see if I have a pointer. Well, we'll do without a pointer. But we initialize this function not with L of x, but with this initial value function V0 of x. And it seems like a very simple change, but it actually decouples the constraint function from the value function that we have at the current space and time. And you can see this as a form of warm starting, where we warm start this solution with a guess. It can be a conservative guess, it can be a too optimistic guess, but with a guess. And the associated formal theoretical definition is that until time zero, we consider the minimum of the trajectory. And then at time zero, so at the final time, we consider the value of the initial value function V0. And so with this comes a couple of nice guarantees. We are still guaranteed that refined CBF, when we solve it iteratively using dynamic programming, it converges to a robust control invariant set. So a set which characterizes safety. And secondly, which is a nice novel theorem that we show, is that when you at some point in time obtain a value function which characterizes a robust control invariant set, if you further refine this control invariant set, because you might have updates on the environment becoming safer, or you're just still expanding what is safe, you retain this control invariance. So you retain safety while you're expanding the horizon of your environment. And so now the question is obviously, how do we deal with unexpected changes? Because I've only talked about the scenario where we have a fixed environment. And so I've talked about the scenario where you start with some initial knowledge, you synthesize or learn a CBF approximation, and you apply Hamilton-Jacobi reachability tools, and you use the CBF. However, one critical insight here is that this value function implicitly captures the dynamics through the trajectory rollout. It implicitly captures the control set you have, the disturbance set, and the failure set through L of X. And so if these values change due to sudden changes, as we said, that you did not model, what you actually want to do is keep this initial guess that you had and use that as a warm-started guess for your updated dynamics. And so just run with that current guess of V with the new updated HA reachability setup. And the way you solve these problems in reality is not this variation on equality. The way it's implemented is with every iteration, you take the minimum between the constraint function and how your value function evolves over time. With, again, the Hamiltonian being defined through the maximally safe action you can take. And so we implemented this on hardware where we can, in real time, adapt to new obstacles. So here we're in a setting where we have a drone. Hopefully it's still visible. And it can see part of the environment, these blue boxes, but it can't see the white Chinese lantern. And this is a change in the failure set, obviously. So as it flies up and it notices that this is the case where it doesn't notice, obviously, that there's a new obstacle, in which case it collides. It's trying to get to this green goal on the right-hand side. Let me skip, for interest of time, this part. But here there's a setting where once it flies over the first obstacle, it identifies this second obstacle and immediately is able to adapt in real time. This is for planar system, so for 4-dimensional system, but adapt in real time to fly under this new obstacle that it found and updated this grid and retain safety. Yeah. So the real-time update here, this is not sped up. So the real-time update is, it can run approximately this HA update. Every HA update, it can run at 10 Hertz on a fairly fine grid, 51 to the power 4 dimensions. Yeah, so we implemented this on a GPU instead of doing it on a CPU, which helps a lot. Yeah, thank you. You have the guarantee that it will converge to a conservative under approximation of the safe set. So not necessarily the same value function, but a conservative under approximation, which at least retains safety. But great question. That's an important point to highlight. And then secondly, we did this as well with I'll skip the baseline here, or I'll just show it for interest. A setting where we're flying with a path planning algorithm to a goal where we have to first fly over an obstacle and then under an obstacle, which is affected by wind, which can be viewed as a change in the disturbance set, D. a second player that tries to push us, as you see here, into this obstacle. And again, here we are able to, let's see, restarting. Our algorithm is able to detect the wind. And here, by detecting the wind, we just tell it at some point that the wind appears. So we're not having a flow sensor on it in this iteration that detects the wind and measures the strength of the wind. But we basically here tell it, hey, there's a wind field, stay robust to it. And as you can see here, the drone tries to stay much further from the obstacle set until it can find a path down that is safe. Now figure out that there's no wind that affects it anymore and continue its path to the goal. And again, this is also in real time. So these updates happen pretty quickly. And obviously, if you were to restart your entire safety analysis, that would not work. So you require this warm starting here to get these convergence guarantees, or not guarantees, but get these nice properties online. And then we've recently also, some of my undergrads moved this beyond having ideal sensors. So consider the setting where we were tying control invariance, in this case by expanding the safe set. So we have a LiDAR, we're in a simulated warehouse environment where the size of the safe set here is like in green. And we have, let's focus on the left-hand side. We have a robot moving through the environment and the safe set growing slowly as it observes more of the environment. But one of the things that you'll see is here is a share of safe cells. And the orange line here is if you were to have learned the share of safe cells offline already. So if you were to have traversed the environment already, and you can see over time that we start approaching the entire safe set, which is very nice. Because so, Inkyu, as you asked, do we have guarantees on getting to the maximal safe set? No, we don't. But in practice, it does happen. And on the right-hand side, we apply this in hardware. Doesn't seem like we can get to that video now. There we go. So we implement this in a setting where we consider some type of construction sites that my undergrads built up late at night before the ICRA deadline, and where it goes to different targets here. Yeah, just submitted last week. So I don't have a lot of information on it to share yet, but yeah, this is basically the work there. Still don't know how to get to the next slide, but trying to click. Maybe this video needs to finish somehow. Worst case, I'll just go to the. Cool. And so in summary, refined CBF is great because it's constructive. It's a constructive method, but it does enable this warm starting. It comes with strict safety guarantees and can be used within a safety filter. And it enables quickly adapting to unexpected changes online. However, at every iteration, you forcibly update the entire value functions at all states, and it does not preserve the structure of the approximate CBF that you might have started with. We did some follow-up work where we only consider patching at certain points. I'll not go into detail, just mention it briefly, where basically the key idea here is that you're only updating these blue cells where you see the safe set decreasing in size. And if you include its neighbors over time, you can also guarantee safety. With many less iterations, and this works great on a CPU, but once you try moving it to a GPU, where now all of a sudden you have a different update size every iteration, it works poorly because you only have a changing set, and that's not as compliant with precompiled functions that you would use on the GPU. So great if you have a very small embedded system. So generally, I'd posit that the remedy to reacting to unmodeled changes in the environment is quickly recovering safety by refining a safety filter while operating online. However, this is limited still in scalability. And so for problems where we want to push scalability further, we want to think about aleatoric uncertainties. And that's the next part of my talk, is adapting offline learned HA value functions for online use. So how can you take into account what can happen online when like learning a value function offline? And for this, I'd first need to introduce some extra ideas about HA reachability. And that's in addition to a failure set, which we've considered, we define where this is the avoid only variation on equality. We define a target set. So a set we want to reach at some time. Implicitly, the interesting thing here is you do not have to solve for all time backwards by having the target set be a control invariant set. So it can be a set that you can flee back to where you already know you have control invariance, so you don't have to solve just based on the avoid problem. So these are called backup sets generally. The associated variational inequality gets very ugly because there's now a max and a min term. But what we showed in some recent work is that if you only consider the instantaneous target reaching and the target set is control invariant, these problems are equivalent. And so we can recover this much nicer form where there's only one min term, which makes it much more amenable to solving with a neural network because there's much less discontinuities that happen. And so we had some work at L4DC this year where we used this setting of having both a target set and a failure set to achieve multiple objectives. And the multiple objectives here is one, staying safe while training, so not crashing into obstacles. But two, at the end of every training episode, you want the robot to return to some state from which you can launch the next training episode, which will make it much easier to train, obviously, a robot from scratch, is that you don't have to come in after every episode and put it back into its place. So we define the obstacles in standard fashion, define the duration of each episode, define this target set as a set of safe reset regions for reinforcement learning. And then we want a time-varying safety filter that ensures that at the final time TE, we are in the target set. And for all times, we're not in the failure set. And then we have a safety filter that is time-varying. Instead of just being dependent on the state, it's now dependent on the time, because at some time you need to get back. And so what this can look like, for example, for this inverted, or I think it's a card pull example, but a card pull, a certain slice of the card pull example, where as time gets closer back to 0, we want to get back to this green set. And so the safe set over time, you can see it slowly shrinking to kind of force you back to this target set. And this worked pretty well, but I'll not go into details. It's not the main focus of the talk. The ideas of using this target set are really useful as well for settings where you might have disturbances in the real world. And so specifically, the setting we considered is a setting in which a robot is deployed in a safety critical environment with both episodically and spatially varying disturbances. What this could look like is a delivery drone that flies in a windy city and has to adapt in real time to this changing wind, both over space and every time you deploy it, there's a different wind pattern. Obviously, learning a value function for every possible disturbance variation across space is infeasible. Assuming the worst case disturbances hold everywhere harms your nominal task performance, and you could never deliver a package anywhere. And lastly, if you only consider that the disturbance is fixed and you just consider a set of different disturbance levels and you just switch between them based on your observations, you might not be able to account for the fact that you're flying into a region where the disturbances are growing, and hence that's what you would ideally want to do, right? You want to be aware that disturbances can grow over time or over space as you move to a certain region, and not doing that may compromise safety. So we cannot represent spatial variations. However, what we can represent are temporal variations. Again, defining obstacles in standard fashion. Choose a target set that is control invariant for the worst case disturbance that you might observe, and solve an ensemble of value functions for different temporally varying disturbance profiles. Here we considered linearly increasing disturbance profiles, but any choice can be possible, exponentially, in any way, shape, or form, or I guess inverse exponentially. And then consider an augmented state space that now, in this case, the second derivative of the disturbance is 0, because we're considering a linearly increasing disturbance. And what this looks like just visually is you might have the blue set be your non-obstacle set under the worst case, under the smallest disturbances, so 0 disturbances, that's your safe set. And your safe set under the worst case disturbances, your target set, is defined in orange here. And so for a small disturbance increase, you might have a lot of time under this assumption to return back to safety. But for a large disturbance increase, you might have to return back to this safe set immediately. And so in practice, what we do is we basically reparameterize online spatial disturbances into temporal disturbances, because we move through the environment spatially, but it gets observed by our system as a temporal change over time. And so offline, we learn an ensemble of safety value functions for systems evolving under different time-varying disturbance profiles. And online, we reparameterize this. So we reparameterize an estimate of the disturbance and its spatial derivative. So its spatial derivative can just be done using finite differencing into its temporal equivalent to query the adaptive value function-based safety filter. So this is the idea of this method, is online, starting from the right, we observe the state we're at, the disturbance, and basically its directional derivative. We reparameterize this into a time-varying disturbance, query the time it would be allowed to get back to what is safe, and use that time-varying safety filter to ensure that we retain safety. Here's the idea: measure the state, update your estimate of the disturbance and the directional derivative here, df of d. Those two together, based on the linear assumption of the disturbance increase, gives you your time to return to safety. You use that to query the value function and its derivatives, and you apply that within the safety filter. The idea here, obviously, is that you would not do this in open loop, but that you'd remeasure your disturbance and disturbance rate. So you're realistic about the present, your current disturbance, but you're pessimistic about what will happen in the future. You kind of assume that the worst case rate of the disturbance change that you've measured in the past will persist until the maximum disturbance. And this leads to really good performance, where if you don't account for the change over time, you crash, as seen on the left side. And on the right side, you can reach all of your obstacles We initially did these experiments with the fans on to mimic actual disturbances, but then for reproducibility had to focus on instead spoofing the drone into thinking that it's at a different location because the drones are very susceptible to vortices. So we now have some updated experiments where we do it with the fans on, but I didn't include these in this talk, I see. So yeah, this is work that I'm presenting on Sunday at Call as well. So no, Sunday during the main conference. This is the main conference. And so the remedy here is solve safety implicitly by finding offline equivalents. And this works as well. This can work as well in an OOD setting where you think of this setting as well of disturbances that you've not modeled explicitly, but you can be robust to by considering that they get worse over time, while not obviously just assuming that they always get worse. And then the third thrust, that some exciting new work that we've been working on over the last couple of months, I still have 10 minutes or something, is scaling HA reachability by leveraging structure. So there's two works that I want to point out here. Here we were interested in seeing these scaling algorithms, so focusing more on deep reach, which we already did for this work that I just presented, but seeing whether you can scale it further and specifically whether you can retain performance as you move to higher dimensions. And so deep reach is a self-supervised neural network that minimizes this variational inequality loss. However, its limitation is that its solution degrades for long horizon problems because there's a lot of there's a lot of local minima that this value that this loss can find. And in addition to that, there's a lack of expressivity of strategy for two-player games. So if we now have two players, so the control and the disturbance, or agent 1 and agent 2, they can find maybe solutions that are correct, but that do not exploit the maximum policies that these agents can take. And so instead, recent work by colleagues at Stanford, mainly Somil and Zeyuan, worked on a sampling-based MPC approach, where the sampling-based MPC, the idea of it is to, over a batch, maximize the cost, basically, that a trajectory obtains over a limited horizon. So over a limited horizon, you just roll out a bunch of samples, and then you take the minimum with the cost to go. So you leverage, in a way, both a more accurate estimate of your value in the short time through sampling-based MPC, and your long horizon estimate of the cost to go from the learned value function. It provides a supervision, like a actual supervision signal to deep reach, which is great, but sampling-based MPC and MPEPI are obviously not good at solving two-player games. So they only work for a single agent game. So we try to advance this and do it for two-player games. And specifically the way we do that, we consider control-affine dynamics. And instead what we consider is that we have one player use a sampling-based MPC approach, and the other player use the optimal approach, like the optimal policy, under the current learned neural network. And this is basically defined by taking the optimal direction in this case that would decrease the value, and so decrease here the cost for the disturbance player, which provides an additional loss sum. But then we can do that for the other player as well, where now we let the disturbance player use sampling-based MPC and let the control player, or player 1 in this case, take the control that maximizes the current estimate of the change in the value function. And none of this, for now at least, is theoretically grounded. However, it works really well in practice. And for example, here what we do is we have several policies compete against each other. We consider two Dubin's vehicles that are one is trying to catch the other vehicle. And specifically, this problem can be solved using classical methods, so using grid-based methods. And we compare how well we perform against these grid-based methods compared to other frameworks that exist. But one is vanilla deep reach, so not using MPC supervision. And one is NISEC, a method developed by Jaime Fizak and colleagues at Princeton. And blue basically indicates that the pursuer that the evader is really good at its job. And so what we can see is that matter, which is our approach, is really good at its job of evading. And also that matter is really good at pursuing, especially when faced with suboptimal agents. So a higher value here in red indicates higher capture. So what we can see, for example, here, this first vehicle tries to catch the second vehicle and is really good at doing that. We also do this for higher dimensional problems for drones, where again, matter is really good at doing this compared to a simple MPC-based rollout and a vanilla deep reach. And we've done this in hardware as well, where the red agent is now the one that's trying to pursue the blue agent. And so it's pretty cool that this works out of the box for it always takes bang bang actions. So it always just takes the optimal control actions. The one thing that we do observe is that it often dives towards the evader, just because that's the optimal behavior, right? Just to dive towards it. But obviously it's not the most stable behavior. But so this works pretty well. We also tried now the case where we have one agent be weaker than the other agent. And for this, just for fun and for publicity, the weaker agent here is the humanoid instead of being a drone, which is obviously much weaker. Where if the humanoid is the pursuer, we can just stay away from it as it tries to catch us. And if the humanoid is the evader, we just hug its butt basically for the entire time. So that's pretty fun, just as an addition there. Then just shifting gears quickly to RL, and a last problem that I quickly want to discuss is we can use HA reachability to define a much broader set of problems. And I'll skip about these control versus fixed policy perspective. That's not really relevant for the discussion. But what we're interested in is not just a reach avoid problem, which is what we defined before, but a reach always avoid problem. Because reach avoid problem, you only care about avoiding until you've reached. Reach always avoid still cares about avoiding after you've reached, which is typically something you'd want. Turns out that's pretty hard to solve for. But here, highlighted, starting from these blue dots in the black dots in the bottom, reach avoid, what might happen is you might be able to reach the blue target, but then you'd crash into the red set afterwards. Whereas solving for this reach always avoid problem manages to avoid the targets even after reaching the target. And what you might want to do is not just reach one of the targets that you're interested in, but reach separate targets, not in a precise order, but in some order. And so that's defined here, where reach, you've only reached one of the targets, and reach, you reach one of the targets, and then your objective is to reach the second target. And it turns out that we can solve these problems through decomposition and turning them basically into forms. The reach always avoid problem can be turned into a reach avoid problem with a special reach objective. And so you can compose these solutions together. And a reach problem can be turned into a simple reach problem, again, with a special objective. Again, combining these. The way you would implement this in reinforcement learning is you'd solve it with an augmented state. Because obviously in reinforcement learning, you optimize over policies instead of control signals. So you need to keep track of an augmented state to account for the fact whether you've already visited one of the goals, because otherwise from one state, you would not be able to distinguish whether you have to go to the goal on the right or the goal on the left. And our idea here is hopefully we're looking at how we can expand this to do a much broader set of problems and actually maybe tackle the whole suite of STL formulations. I'm co-leading that, not one of the main leads. So other people are way more mathematically smart than I am and are working on this, but it's an exciting direction to move into. And we outperform constrained PPO and STL-based baselines, where again, with this decomposed solution for half cheetah, we are able to achieve reach 2 and achieve both goals, where it jumps up to the first goal and then manages to quickly reach the second goal. One of the things that was really important to get good performance here is that you kind of want to warm start the joint solution with the decomposed solution with the trajectories that you observed from the joint solution, because they're all coupled in a way. So you don't want to train these three solutions separately, these three value functions, but you want to do them jointly. Obviously, they still have their own weights, but you do want to train jointly to be able to initialize smartly. So yeah, that's all that I have today. A kind of a journey of the last 2 years of my PhD. Want to give a shout out to my incredible lab and the collaborators that I mentioned both today and other collaborators from other projects. Thank you for your time, and I hope it was an interesting talk, even for Friday afternoon. Any questions?
Training value function just neural network with neural network.
So no, so for the deep reach based approach, yeah, you just use vanilla neural network, just MLPs. Yeah, no, just MLPs, and even for the RL approach, it's just MLPs. But you can obviously, it's very easy, and people have shown that you can, if you want to start with an image, you can use, like with video inputs, you can use a transformer, but followed by MLPs. One of the important things for getting deep reach to work, because it's self-supervised, it actually benefits from sinusoidal activation functions, both for differentiability and to work well. But obviously, if you scale it to RL, what you want to do is just have ReLU activation functions. Other questions?
Or from online.
I see some mentions in the chat.
That's yeah. Thank you. You're grateful. I have some questions.
Yeah.
So, well, thinking about
Mm-hmm.
was I believe in many
Uh-huh.
So as you said, a lot of the dynamic that
Yeah.
often happen. Any of them.
No, all of this hinges again on kind of being able to measure changes, measure them in some way, shape, or form. So either, obviously, for the constraint set, that's easy, can just be a LiDAR or camera sensor. Yeah. But for indeed, loss of actuation might also be easy. But indeed, detecting whether a certain wind event is a aleatoric uncertainty or an epistemic uncertainty, that's much harder. And that's not something that I've focused on mainly. I've mainly focused on once you can measure changes in disturbances, how do you treat them? But yeah, it's a great question. To implement this in the real world, you have to think about. Yeah. Yeah, so I mean, so the real-time updating always hinges on the fact that you're doing dynamic programming. So it's limited in scalability, right? So I haven't done any work on like real-time fine-tuning. What could be interesting for real-time fine-tuning is have the last layer of your neural net be some probabilistic layer, and for example, having just a linear set of weights that you can update based on the observation in the environment. So some form of a last layer Bayesian neural net. But more generally, for the deep reach setting, what we did consider here is parameterized deep reach. So we parameterize here over the disturbance rates. And so based on different disturbance rates, d dot small, d dot large, that we observe, we have a longer or shorter time to get back to this safe set. That makes sense. But being able to reason about like, how certain am I that this added wind is just a freak event or will persist into the future? Like I've not, as I said, I'm mainly focused on the decision-making part, not actually the estimation and the prediction part. I think where it's much more interesting, which is a project that we are working on as well now, is just on a tangent. So I've talked a lot about these zero-sum games, where basically one agent always tries to catch the other one or tries to get the other one to fail. If you talk about two agents, that means the one agent catches the other one and tries its best to ram into the other agent. Obviously, on a highway, that's not how things work, right? The other agents might not share your objective of not crashing, but might just not care a lot about it. But the opposite of this zero-sum game, as we call it, where it tries to crash into you, is a cooperative game where it does everything it can to get out of your way. And so what we're considering now actually is just a linear parameter between those two. So can you somehow linearly parameterize between a zero-sum game and a fully cooperative game? And their online estimation is much easier. You just use a particle filter, see how well their objective aligns with yours, and use it online. We tried submitting that to ICRA, ran into a couple speed bumps along the way. Now we're submitting it, I think, to L4DC, hopefully. But I'll share that once I have results on that. So in some settings, it's much easier to do that. But for wind's really hard to actually do that. Mm-hmm. Yeah.
And in addition, I haven't considered that. With some idea of the very complex.
Mhm.
venue plus current from that.
Mhm.
Then
Mm. So you need to be able to proactively decide about the wind. Yeah, I think that's a great point for practical use cases. I think partially with safety filters, the challenge is that it can only be like safety filters provide an instantaneous change to your control. Obviously, when you start thinking about or incorporating in your safety filter that disturbances or that the wind will grow, it becomes a bit smarter in a way in that it can reason about the future. But it might still be limited in real long horizon settings where you realistically care about such a. Cool.
thank you again for coming with us today.
Yeah. Yeah, feel free to, Namun, feel free to share my email with people. And
Yeah, thank you for coming online. Thank you.
thank you, Namun, as well for organizing today.
Okay.
Yes.